a moon that travels backward around its planet, a dwarf planet whose two halves circle a point in empty space, a world buried so deep inside a multi-star system it could, in theory, look up and see 7 suns. None of this is science fiction. Every one of these things exists somewhere in our own solar system or in the strange, star-crowded neighborhoods scattered across the galaxy. Stick around, because by the end of this video, something as basic as an orbit will look a lot less simple than it did a few minutes ago. When most of us imagine a solar system, we picture one glowing star sitting patiently in the middle while everything else loops around it in tidy circles. That arrangement really is the most common setup in the universe, but plenty of systems ignore that blueprint entirely. The moment you dig into how orbits behave across the cosmos, you start finding arrangements that feel closer to chaos than clockwork. Let's begin with systems built around more than one star, places where 2, 3, or more stars are locked in a gravitational tug-of-war instead of one star calmly anchoring everything else. What happens to any planets caught in that crossfire? Can a planet even hold a stable path while multiple stars pull on it from different directions? The answer is yes, though there's no single template for what those orbits look like. It helps first to understand how multi-star systems stay together at all. Most stable configurations settle into a layered, hierarchical arrangement, largely a byproduct of how closely those stars originally formed. A simple 2-star setup is easiest to picture. 2 stars looping around their combined center of gravity, the barycenter. When both stars carry roughly equal mass, the orbits tend to be fairly balanced ellipses, occasionally nearly circular. When one star massively outweighs the other, the heavier one barely budges from that shared center while its lighter partner swings much further out. Push beyond simple pairs and you find systems with 3, 4, 5, 6, or even 7 stars bound together, with a clear organizing principle keeping them from flying apart. In a 3-star system, 2 stars are usually locked into a tight pairing, with the third looping around the pair's combined mass. This keeps things stable, because if all 3 shared crossing paths, one would eventually get flung out entirely. Add a 4th star and possibilities multiply, sometimes 2 close pairs orbiting each other, sometimes one pair alongside 2 lone stars. Push toward 5, 6, or 7, and arrangements become genuinely elaborate, though anything beyond that grows exceptionally rare, since crowded systems struggle to stay stable long term. So what happens if you drop a planet into a system this complicated? Could a world genuinely have 7 suns in its sky? Believe it or not, yes. Imagine a hypothetical 7-star system built from 3 clusters, a tight pairing of 2 stars, plus 1 lone star nearby. A planet circling only that solitary star would see just 1 sun overhead. Further out, planets orbiting the entire 3-star cluster would technically have 3 suns. And at the very edge of the structure, a planet could orbit all 7 stars as a single unit, becoming a genuine 7-sun world. Viewed from far enough away, a system this complex would visually collapse into something resembling a simple 2-star pairing, since each cluster would blur into one bright point. That outermost 7-sun world would sit so far away that none of its suns would deliver much real heat or light, appearing as scattered, faint points rather than blazing companions. Move inward toward the planet circling the 3-star cluster, and those suns would appear larger and brighter, giving that world a genuine day and night cycle, with the distant cluster flickering slightly as its members drift closer and further apart. Finally, picture a planet locked tightly around the single lone star, close enough to become tidally locked, permanently showing one face toward its sun, its shadowed far side occasionally catching stray light from the distant pair. This raises another question. How many star systems actually contain more than one star? Is our single-star setup the outlier or the typical outcome? Look up at a genuinely dark sky and you might be surprised how many of the brightest points are actually multiple stars locked together. Sirius, the brightest star visible from Earth, is a binary. Alpha Centauri, our closest stellar neighbor, is a 2-star system, or arguably 3, counting its smaller companion, Proxima. Even Polaris turns out to be a binary too. For a long time, that pattern led astronomers to assume our lonely setup was the exception rather than the rule. As observing technology has advanced, though, it's become clear most star systems across the galaxy actually contain just 1 star. Part of why the brightest stars skew toward multi-star systems comes down to brightness itself, since 2 stars combined put out more light and are easier to spot. It also matters that roughly 85% of all stars are small, dim red dwarfs, and only around a quarter of those have a companion at all. Multi-star arrangements show up far more often among massive, hot blue and white giants. Red dwarfs never gathered enough material to grow larger, while blue giants often form alongside other stars from the same collapsing gas cloud, in nurseries that are genuinely turbulent until rough order settles in. Leftover material around these stars later forms planets, though that's far tougher in such a chaotic environment than around one calm star. Difficult doesn't mean impossible, so a genuine seven-sun planet may really exist, and imagining its sky makes for a fun thought experiment. Let's shift now from theoretical multi-star worlds to something sitting right in our own solar system, out at the far edge of Saturn's gravitational reach. Saturn itself is instantly recognizable, and moons like Titan, Enceladus, and Rhea circle it in an almost clockwork rhythm. But millions of kilometers further out, there's a moon that doesn't fit the pattern. Dark, heavily scarred, moving in reverse against everything else nearby. This moon is essentially a frozen leftover from an era when the giant planets were still shuffling around and the young solar system was tearing itself apart, covered in ancient landslides and pockets of frozen carbon dioxide, and sitting inside a hidden ring of dust so massive it dwarfs Saturn itself. This moon, Phoebe, genuinely shouldn't be there. A wanderer captured by Saturn's gravity and held prisoner for roughly 4 billion years. Phoebe's story begins with a technological leap. For most of human history, astronomy was limited to what the naked eye, and later a telescope, could pick out directly. That changed in the 19th century when dry plate photography let astronomers leave a shutter open for hours, revealing objects thousands of times dimmer than anything seen before. In 1898, a Harvard College observatory team led by William Henry Pickering set up in Peru, running a deep photographic survey of the southern sky. In 1899, reviewing plates from the previous August, Pickering spotted a faint speck roughly 4,000 times too dim to see unaided. It moved alongside Saturn night after night, yet behaved differently from every other known moon. In March 1899, Pickering formally announced the discovery of Phoebe, the first moon ever found, through photography rather than direct observation. As astronomers tracked this moon into the early 20th century, excitement gave way to confusion because Phoebe wasn't just distant, it was fundamentally out of place. Almost everything in our solar system formed from the same swirling disk of gas and dust, so planets and moons overwhelmingly orbit and spin the same counterclockwise direction. Phoebe breaks that entirely, circling Saturn clockwise, opposite the planet's rotation and every other major moon nearby. Astronomers call this a retrograde orbit, and a moon moving backward like this almost certainly didn't form where it sits. Had Phoebe formed from gas and debris around a young Saturn, drag from that material would have pulled it into a normal forward orbit. A backward orbit is a smoking gun pointing toward a violent origin story. Phoebe likely formed elsewhere and was later captured by Saturn's gravity. The distances involved are staggering. Phoebe orbits at an average distance of nearly 13 million kilometers from Saturn, taking roughly 550 days, about a year and a half per lap. It sits so far out, you wouldn't spot Saturn's rings with a naked eye from its surface, just a small point of light in an otherwise dark sky. Right? Because of that distance, Phoebe went largely uninvestigated for close to a century. Even Voyager 2, flying through in 1981, only caught a distant, jagged, dark blob from over 2 million kilometers away. We knew Phoebe was strange, but had no real detail, not until Cassini arrived. While plotting Cassini's approach into Saturn's orbit, engineers realized the spacecraft would need to slow considerably, and that this trajectory offered one unrepeatable chance to swing close by Phoebe first. The flyby happened in June 2004, roughly 19 days before Cassini's critical engine burn locked it permanently into orbit, since afterward there'd never be enough fuel to circle back. For a handful of frantic hours, this dark little moon transformed on camera from a distant dot into a genuinely complex world, the spacecraft racing past at nearly 6 kilometers a second before Phoebe faded back into darkness. The images revealed a world unlike anything else nearby. Phoebe is roughly spherical, about 213 kilometers across, but looks thoroughly battered, reflecting only around 10% of sunlight, about as dark as fresh asphalt. Cassini's cameras mapped extensive cratering and brightness variations, while instruments detected water ice, carbon dioxide, iron-bearing minerals, and chemical signatures consistent with primitive, carbon-rich material typical of outer solar system objects. One massive impact basin, roughly 100 kilometers wide, covers nearly half of Phoebe's diameter, and surviving an impact that's severe means it must be a solid body rather than loose rubble. Even more striking were the landslides. Gravity on Phoebe is weak but strong enough that impacts destabilize crater walls, and Cassini spotted bright streaks where darker material had slumped away, revealing lighter material underneath, confirming Phoebe is a dirty, ice-rich body coated in a thin layer of dark dust. The real key to understanding Phoebe came from its density, calculated by tracking how much it tugged on Cassini during the flyby, roughly 1.63 grams per cubic centimeter, versus about 1 gram per cubic centimeter for Saturn's mostly ice-regular moons. Phoebe, by comparison, is somewhere between half and two-thirds rock, a density similar to Pluto and Neptune's moon Triton, suggesting it's essentially a planetary embryo, a small world that had begun separating into a rocky core and icy mantle before that process got interrupted. Detecting carbon dioxide trapped in its surface rocks reinforced this, since on Saturn's warmer moons that compound would have boiled away long ago. Its presence suggests Phoebe formed in the deep freeze far beyond Neptune, before wandering inward and getting permanently snared by Saturn's gravity. Phoebe's story doesn't end with capture either. For billions of years, this dark moon has endured a relentless rain of tiny micrometeoroid impacts, each blasting a bit of dark surface material into space. Because Phoebe's gravity is weak, that dust easily escapes and settles into its own backward orbit around Saturn. Over billions of years, that accumulation built a structure that remained hidden until 2009, when astronomers using the Spitzer Space Telescope discovered what's now called the Phoebe Ring. This ring is genuinely enormous, invisible to the naked eye, but glowing in infrared, stretching from roughly 6 million to 16 million kilometers from Saturn, large enough to fit roughly a billion Earths inside. Seen from Earth, it would appear roughly twice the width of our full moon, making it the largest ring structure in the solar system, with Phoebe orbiting right through its middle. The dust is spread so thin it's essentially invisible in reflected sunlight, which is why Spitzer detected it only through faint thermal glow. The ring sits tilted roughly 27 degrees relative to Saturn's main ring plane, matching Phoebe's own tilt and backward motion, and its chemical signature matches the dark material coating Phoebe, confirming ongoing micrometeoroid impacts have fed this diffuse dust halo for billions of years. This discovery also solved one of astronomy's oldest mysteries. Back in 1671, astronomer Giovanni Cassini discovered another Saturnian moon, Iapetus, and noticed something strange. One hemisphere bright white, the other almost coal black. We now understand why. Iapetus orbits Saturn forward while Phoebe orbits backward, and as dark dust from the Phoebe ring spirals inward, it slams into Iapetus's leading edge as the two moons pass each other, coating one hemisphere in dark material and producing the contrast that puzzled astronomers for 3 centuries. So how did a dark, dusty moon that likely formed far beyond Neptune end up trapped closer to the Sun at Saturn? The leading explanation suggests that around 4 billion years ago, the giant planets went through a period of dramatic migration, violently disrupting the primordial belt of icy debris beyond Neptune. Countless icy bodies either plunged inward or got flung out of the solar system entirely. But a lucky handful, including Triton and Phoebe, ended up captured instead, becoming permanent moons of the giant planets they encountered. Phoebe, in that sense, is far more than an oddly behaving moon, a preserved relic of the raw building blocks that formed the outer solar system, frozen in place by Saturn's gravity, and a reminder that planetary systems are dynamic, letting objects wander enormous distances and leave a permanent mark far from where they began. Let's zoom out even further, past every planet and moon, to the very edge of our solar system, where a colossal, mostly theoretical structure is believed to encircle the Sun and everything orbiting it. Picture a shell of billions, possibly trillions, of ancient icy chunks roughly the size of small mountains, marking the outermost boundary of our solar system, at least according to the leading theory. This region, sitting beyond the reach of even our most powerful telescopes, is known as the Oort cloud, and it remains one of the most compelling unsolved mysteries in modern astronomy. Most people have heard of the asteroid belt, and probably the Kuiper belt too, 2 donut-shaped rings of debris orbiting roughly in the same plane and direction as the planets. The asteroid belt sits close to the Sun, wedged between Mars and Jupiter. The Kuiper belt sits much further out, past Neptune, proposed as the likely source of short-period comets, which complete an orbit in under 200 years, along predictable paths. Around that same time, Dutch astronomer John Oort was investigating a different puzzle, the origin of long-period comets, which take millions of years per orbit and arrive from every direction rather than one plane. Oort noticed something unusual when he traced their farthest point from the Sun. It clustered around the same enormous figure across nearly every comet he studied, somewhere around 50,000 astronomical units, 1 astronomical unit being the average Earth-to-Sun distance. Neptune sits at roughly 30 astronomical units, and the Kuiper belt extends to only around 50 at most, so this sat vastly further out than anything previously mapped. Based on this, Oort proposed an enormous, roughly spherical shell of icy debris surrounding the solar system, a reservoir that could explain where these comets originate. In the decades since, mathematical modeling has continued supporting the theory, with astronomers refining how it likely formed. The leading idea is that it formed from leftover debris dating back to the solar system's formation roughly 4.6 billion years ago. As planets took shape, gravitational interactions flung much of that material outward. Some was ejected entirely, while a significant portion settled into wide, eccentric orbits still loosely bound to the Sun. Occasional gravitational nudges, whether from passing stars, drifting molecular clouds, or the Milky Way's broader pull, are believed to periodically knock distant objects inward, eventually appearing to us as long-period comets. Roughly 70,000 years ago, a small binary system known as Schultz's star grazed the outer edge of the Oort cloud, becoming the closest known stellar visitor on record. It caused no major disruption, since a binary of a red dwarf and brown dwarf carries far weaker gravity than our Sun, though 2018 simulations suggest it still nudged a handful of Oort cloud objects out of place. The Sun has existed over 4 billion years, so other close encounters have almost certainly happened, though current models suggest none prevented the Oort cloud from forming. Some researchers believe similar Oort clouds exist around other stars too, and that ours may consist of two regions, an inner, flattened disk similar to the Kuiper belt, and an outer portion forming the classic spherical shell most people picture, together spanning perhaps 2,000 to 100,000 astronomical units, or more than 1.5 light years across. Voyager 2, traveling outward since its 1977 launch, has covered roughly 139 astronomical units so far, crossing beyond the heliosphere in 2007 and into true interstellar space by November 2018. Yet it would still need another 300 years just to reach the Oort cloud's innermost edge, and tens of thousands more to cross it, a reminder of how vast interstellar distances are, given that our nearest stellar neighbor, Proxima Centauri, sits over 4 light years away. Not every astronomer is fully convinced the Oort cloud exists exactly as described, since we've never observed it directly. Some argue long-period comets could instead originate from interstellar space entirely. A theory that gained traction in 2019 when an amateur astronomer discovered the first confirmed interstellar comet, its chemical composition suggesting a different star system of origin. Still, most astronomers continue supporting the Oort cloud theory since indirect evidence and modeling both point that direction. Part of why we can't see it directly comes down to sheer scale. Individual chunks are mountain-sized, while the distances separating them are almost incomprehensibly vast, relying entirely on faint reflected sunlight, too weak to detect that far out. Sticking with strange orbital behavior, consider Pluto and its large moon Charon, which don't orbit each other quite as you'd expect. Instead of Charon simply circling Pluto the way our moon circles Earth, the two bodies orbit a shared point sitting out in open space between them. Every orbiting pair technically circles its own barycenter, the shared center of mass. For Earth and its moon, that point sits so far toward Earth's mass that it remains buried inside our planet, which simply wobbles as the moon tugs on it. Pluto and Charon are much closer in mass, pushing their barycenter completely outside Pluto, creating the striking effect of both bodies swinging around an apparently empty point in space. The only other major pairing where this happens is the Sun and Jupiter, whose tug shifts their balance point just outside the Sun's own surface. Even the stars filling our night sky don't move quite the way most assume. Surveys mapping hundreds of thousands of nearby stars show that while many broadly drift together through the galaxy, plenty head off at wildly different angles, some slowly drifting out of the galaxy entirely. Over time, these stellar neighborhoods spread apart and reshuffle, though density patterns within the galaxy's spiral arms periodically pull scattered stars back together. And the brighter clusters we can pick out tend to share similar velocity and direction for surprisingly long periods. And finally, one planet doesn't orbit strangely so much as it simply spins on a bizarre angle. Uranus, positioned second farthest from the Sun, it remains one of the least explored planets, and its strangest feature is its axial tilt. Our solar system formed from one rotating disk of gas and dust, and everything started out spinning roughly upright relative to the plane it settled into. Uranus almost certainly began the same way, but early on it appears to have collided with something substantial enough to knock its axis over to roughly 98 degrees, tipping the planet onto its side. Rather than spinning upright like Earth, tilted only about 23.5 degrees, Uranus effectively rolls along its orbital path, producing bizarre seasons across its 84-year orbit. For roughly a quarter of that orbit, one pole points almost directly at the Sun, while the equator receives little direct sunlight. When Voyager 2 flew past Uranus in 1986, it caught the planet with one pole pointed nearly straight at the Sun, finding remarkably little visible weather, none of the swirling bands familiar from Jupiter. That apparent calm turned out to be simply tied to where Uranus sat in its sideways orbit at that moment. 2 decades later, Hubble observations revealed considerably more active weather, confirming its position along that tilted path dictates what becomes visible. Uranus does host winds reaching roughly 800 kilometers an hour, mostly hidden beneath its atmosphere, but detectable using infrared. Features Voyager 2 never got to study during its brief flyby. No spacecraft has returned since, and plenty of questions about Uranus's strange history remain unanswered. From backward moons and sideways planets to invisible reservoirs of icy debris and dwarf planets circling empty points in space, our own solar system is packed with orbital behavior. that breaks nearly every assumption you might casually walk in with. That's really the point of paying close attention to this kind of astronomy. The universe rarely settles for the simplest possible arrangement when a stranger, more complicated one, turns out to be equally, or even more, stable over billions of years. If any of this shifted how you picture orbits working across the cosmos, that's exactly the point, because there's always another strange corner of the universe worth exploring.